Hey folks, welcome to video number 2. This one is all about slashing on Ethereum. Specifically, I'm going to cover the difference in slashing post-Pectra versus pre-Pectra to see what's changed. Basically, the conclusion is that the slashing penalty has gone down overall post-Pectra. I'm going to walk you through where in the specs that's happened. Basically, it's the initial slashing penalty, and then the proportional slashing multiplier is going to be typically higher, but in total, the slashing penalty is a little bit lower. So I'm going to walk through that. But before I do, I want to talk a little bit about slashing on Ethereum and slashing generally. So on Ethereum, slashing is like any other network. It basically comes down to what's called equivocation or double signing. Double signing just means that as a validator on Ethereum, you're saying two or more things exist at the same time. And you can appreciate, if you think about consensus mechanisms with millions, well, around 1 million validators today on Ethereum, if you're trying to reach consensus across 1 million validators or even only a handful of validators, but each validator is saying a few things exist at the same time, it's just not possible. And so that's part of the reason that you have this equivocation or double signing condition on Ethereum. But maybe taking one step back, it's helpful to be reminded of the different tasks that validators can be asked to perform. So there are 3 general tasks. One is to attest. So basically, attesting is just saying, here's what Ethereum looks like to me. You report a few pieces of information. I'm going to show you that in the specs, what those pieces of information are. But attesting is just saying, this is what Ethereum looks like to me. Proposing is actually building a block. So you gather a bunch of transactions together and you propose a block to the network. The last one is sync committee participation. That's a little bit different. It kind of looks like attesting, but you provide less information when you participate in sync committee. But attesting really is the one that the validators are doing on a regular, consistent basis. So there are 225 epochs per day on Ethereum. Each epoch is subdivided into 32 slots, and each slot is 12 seconds long. Think of a slot as the potential for a block, but not necessarily a block. Validators are expected to attest every epoch. So again, there are 225 epochs a day, so a validator that's running well will attest 225 times per day. Proposals, on the other hand, a single validator is expected to propose once every 5 to 6 months. And you can get an intuitive sense for this if you think about the fact that there are basically 7,200 slots per day. And again, slots are the potential for a block, but not necessarily a block. And in practice, it ends up being, you see something like 7,150, 7,160 blocks per day. So there's 40 to 50 slots that are missed typically in a day. But just say for the sake of roundness that there are 7,200 blocks in a day, and there are something like 1,050,000 validators today. So you can appreciate that if there are only 7,200 blocks in a day and 1 million validators, you can start to get a sense of how the math works out to roughly once every 5 to 6 months. Sync committee participation is even less frequent. That happens, one single validator is expected to participate in sync committee once every, I believe it's 5 to 6 years. And the reason for that is sync committees last for 256 epochs, which is a little over a day, 27.3 hours. And there are 512 validators chosen to be part of that sync committee. So again, you can kind of do the math given the numbers. We have over 1 million validators today. Only 512 are chosen for any 256 epoch period. Anyway, put all that aside, and we got to get back to slashing. So there are 2 ways that a validator can commit a slashable offense. And that has to do with when they're attesting or when they're proposing. And remember, a slashable offense is equivocation or double signing. So in other words, when it's a validator's turn to attest, for instance, if a validator says that two or more things exist at the same time, they're mutually exclusive, that's a slashable offense. Another example is on the proposal side. So forget about testing now and think about proposing. When a validator proposes a block, if they propose 2 or more blocks that differ in any way. So when it's their turn to propose, if they propose more than 1 block, in other words, 2 or more, and they differ in some way, that is a slashable offense. So let me share more specifics here. So I'll share my screen. So first thing, I just want to show you on the proposal side what this actually looks like in the specs. And note that the specs I'm going to look at are for beacon chain. That's phase 0. So if you watch my last video, I went through the specs a little bit and talked about how they work. And phase 0, and I talked about all the forks. And when things change, you'll see the specs for those, and it'll outline the changes. But a lot of the aspects about slashing, especially the conditions that are a slashable offense, have not changed since the launch of beacon chain. So almost 5 years now, since what, late 2020, I guess. So that's why I'm referencing. You'll see up at the top here. Let me zoom it in a bit so you can actually see what I'm talking about. You can see kind of at the top, that's a little more clear, I guess. But you can see phase 0 is what I'm talking about. Let me just see. I just lost the slashable. Here we go. Proposer slashings. So I talked about both slashing on the proposer side and on the attesting side. I'm going to start with proposals so you can see what that looks like. So basically what's happening here, this function, process proposer slashing, it's checking a bunch of things. You can see the first few parts here, assert header 1.slot equals header 2.slot. In other words, if you're a proposer and you've been selected to propose a block in a particular slot, this condition is just making sure that the block you're proposing, so let's say you propose 2 different blocks, that's header 1, header 2, and the slots are the same, then there's a chance you've committed a slashable offense. In other words, you've got 2 different blocks out there, and again, the header 1 and header 2 is it's referring to an element of the block, not the full block, but an element. I'm going to come back to that in a minute. But these checks are basically looking to make sure that you've proposed 2 different blocks at the same slot, and then you can see here the second condition is just checking, is it the same proposer? So same proposer proposing more than 1 block, and then here is the check for the slashable offense, which is basically the 2 headers differ in some way. And that's effectively the slashable condition there. This next condition, proposer equals state, validators header 1 proposer index. Okay, so I think there's some condition here. We can take a look at this. Is slashable validator. So basically, oh wait, let's actually see the function here. Okay, so here you can actually see the condition is slashable validator, what's being checked. So those first few conditions, we're basically saying, is it the same slot? And you have 2 blocks, basically, those headers I was talking about. Is it the same validator? And then the last thing to check is, or sorry, and do the blocks differ in some way? And then the last thing is the validator slashable? So it seems like is slashable validator is really the check that's happening, but it's more of like a technical check that's being done. And you can see what's happening here. So this not validator.slash, this means what this condition is checking is that has the validator already been slashed? So you're not going to get slashed twice. And validator.activation epoch is the validator's has already been activated. And then this last condition here is just it's not already withdrawable. So there are a few. This last piece is really less important than the first 3 that I outlined. So first, again, is it the same slot? So are these 2 blocks happening at the same slot? Is it the same proposer that's proposing them? And then do they differ in any way? Those are really the key conditions for a proposal. I also want to show you, though, the beacon block header. Now, this is not what's actually being compared, but it's part of what's being compared. So what's actually being compared is the signed header, which does contain this data, though. So if I actually showed you the signed header, it wouldn't be that illuminating for you. So I wanted to show you what's contained in the beacon block header. And I believe there's more data today than there was. This is phase 0. So some things I believe have been added here. But you can see slot, proposer index, and then 3 different roots, parent, state, and body. But if any of those things differ, except for the first 2, because remember, those are already being checked to make sure that they're the same. And then if any of the parent, state, or body root differ, then it's a slashable offense. So in other words, again, you can see how this kind of ties back to the slashable, the definition of a slashable offense as equivocation. When you're the proposer, if you produce or if you propose 2 or more blocks in the same slot and they differ in any way, you've committed a slashable offense. And so you can kind of see when you look at each of these pieces how that ties back to that definition. So let's move over now to the attestation side. And one thing I'll show at the end, you can see how many slashable incidents have occurred so far. So we're in the beginning of July 2025. And the last I checked, probably about, I don't know, a handful of weeks ago, there were a little under 500 slashable incidents that have been committed on Beacon Chain since its launch. So it's around 100 slashable incidents every year. Now, that's just taking a simple average. They're obviously going to be clustered in different time periods, so it's not going to quite work out that way. But as a rough approximation, you can look at it as roughly 100 slashable incidents every year. So not a ton. And also, if you look, I mentioned the 2 different categories of slashable offenses. One category is on the proposal side, the other is on the attestation side. Around 95% happen on the attestation side. And you can kind of appreciate why that's the case when you think about how much more a typical validator is going to attest than it's going to propose. So it's going to attest 225 times per day, but it's only going to be expected to propose once every 5 to 6 months. And so again, you can just think about a day and you can think about how many proposals there are versus how many attestations there are, right? So every validator is attesting 225 times per day, and there's over 1 million validators. Whereas they're only going to, at most, there's going to be 7,200 proposals a day. So you can kind of get a sense why you would expect to see more violations on the attestation side, all else equal and not considering anything else. Anyway, so we've talked about proposals. Now let's look at attestations. And here is the function that checks for slashable attestations. And you can see the 2 different, or you can see 2 different conditions here. Double vote, that's equivocation. Double signing, double vote. Surround vote. I'm going to come back to surround vote in a second. So looking at the second part, the second condition that's checked, data_1.target.epoch equals data_2.target.epoch. What this is saying is you have 2 different pieces of attestation data. In other words, 2 attestations. I'm going to show you what those look like in a minute. But basically, when I talked about equivocation, I framed it as saying 2 or more things exist at the same time. This condition is checking at the same time. And the way it's doing that is it's saying, I have these 2 attestations. When did they happen? During which epoch? And that's the condition that's being checked. And the first part is just basically saying, given that these happened at the same time, does the data differ in any way between those 2 attestations? So that's the double vote. So just to tie back to proposals for a second, if you remember when we were looking at proposals, I'll pull that back up so you can actually see it here. Oops. This one will not be that. Here. We'll come right back to the attestation in a second. You can see this is on this check right here is checking the slot. The reason that happens is that there's only 1 proposer per slot. So the slashable conditions on the proposal side are checking on a slot by slot basis. However, I mentioned epochs when talking about attestations. We'll go back here. And apologies to American friends. I'm Canadian, so I say epoch, so just bear with me. You can see here, this condition, it's checking 2 different epochs. Now, again, a validator is only expected to attest once per epoch, and that's why the granularity of the time when checking on attestations is broader than for proposals. Proposals is every slot. There are 32 slots in an epoch, but a validator is only expected to attest once per epoch, and that's why, again, that's why we're checking epochs here. So I'm going to discuss surround vote as I'm showing you what attestation data looks like. So here's what an attestation looks like, or the data structure, I should say. I believe this has changed as well since phase 0, but the concept is largely the same. So you've got slot, committee, index. The idea here is that all validators, even within a particular slot, so validators chosen to attest, let's say it's chosen to attest in the 3rd slot of that particular epoch, it's then further grouped into a committee. And so there are multiple committees within a particular slot. So the idea is just to roughly get the same number of validators in various committees within a slot. So epoch is divided into slots, and slots in terms of attestations are further divided into committees. But you can ignore that for the purpose of this discussion. And then you see the data. You have a beacon block root, you've got a source and target checkpoint. The way to think about checkpoints is that they demarcate epochs. A checkpoint is basically the block in the 1st slot of that particular epoch. So that's the way to think about a checkpoint. And there's a little rule in there because sometimes you have empty slots. If there isn't a block in the current epoch, you look to the prior epoch, and the block in the 1st slot of that epoch is a checkpoint. So anyway, and it's recursive, so it keeps going until it finds a block in the 1st slot of an epoch. So anyway, that's the way to think about a checkpoint. And you can appreciate that if the checkpoint is indicating a block within an epoch, just one block, that is the block in the 1st slot of that epoch. When you start looking at a bunch of checkpoints, you can basically, you're dividing epoch by epoch. The source and the target help Ethereum reach justification and finalization. I'm not going to get into that in this video. I will do another one potentially about justification and finalization and how that works. I mentioned in my last video the annotated specs by Ben Edgington. He not only has the annotated specs, which are awesome, but he also has a bunch of notes on Ethereum's consensus mechanism, for instance. So highly recommend that, and he'll give a better explanation than I would for the checkpoint. So highly recommend to check that out, and I'll drop a link to that. But anyway, one more thing to say about the checkpoints. Actually, let's go back to the attestation. So you've seen checkpoints, you have a general sense of what they are, even if it's not a super firm grasp. Let's go back to the surround vote. So here you can see the source and target, and that relates, let's go back, source and target. That's what we're talking about here. Basically, the idea is that you can have you can vote your source and target such that your one attestation entirely surrounds another one. So in other words, you can see here data 1 and data 2, those are just attestations. So when you see data 1, think attestation 1, data 2 is attestation 2. And you can see there's source and target, okay? So here what we're saying is data 2 or attestation 2, the source and the target are completely surrounded by attestation 1. And you should appreciate, sorry, one other thing I should mention, source comes before target. Okay, there's like this link that's created when you have a source and a target. So coming back to the attestation, we have our surround vote, and I talked about the checkpoints for the attestation. I'm just going to go back and show you real quick. You can see here, source checkpoint, target checkpoint. And basically a surround vote is when one source target link completely surrounds another. So again, when you look here, you can think of data 1 as attestation 1 and data 2 as attestation 2. And notice that the source for the first attestation is less than, in other words, it happened before attestation 2, but the target for attestation 1 happened after attestation 2. Now that's all very confusing. I'm going to do a separate video for this. I could spend a good chunk of the remainder of this video just talking about surround votes. It's not a simple concept to grasp, at least in my opinion. Maybe others have found it easy, or maybe others have explained it in a better way. But I will do a separate video specifically for surround votes to try and explain those a little bit better. But From a high level, this kind of gives you a sense about what the slashable conditions on Ethereum are. Again, it's about equivocation or double signing. That can happen in one of two ways. Either you're proposing a block or you're attesting to the state of Ethereum. And it ultimately boils down to saying that two or more things are true at the same time. A few other comments might be helpful. You know, I've talked about historically what we've seen for slashing. And by the way, I might as well just show you a link now. So Beacon Chain, if you go to validators, you go to slashings, and let's go 100 per page. So you can get a sense. I mentioned roughly 500. I think it's like 480 something, 490 something, 484 entries. I think there's one or two double entries. So it's either 485 or 486 in total. So you can see various bits of information here. So how old is it? When did it happen? This one happened on June 30th. What was the reason? So of those two that I mentioned, proposal or attestation, which kind is it? In this case, it's an attestation violation. And as I mentioned previously, we would expect to see more attestation violations than proposal violations, all else equal. But anyway, you can go there. I don't know if it's so easy to see. Oh, you can't really see it all. Anyway, this is the address here. And then you can just go when you get to the landing here. I'll go back to the landing page. Here's the landing page. And you can see again, almost 1.1 million validators active today. You can see there's a bit of a queue. Anyway, at the top here, you can see validators. Maybe I'll zoom in a bit more. Better view. Let's go maybe a few more. There we go. Validators. You just go here in slashings. And that's how I got to that. And this is the link. I mean, I'm assuming, well, anyway, added that out as well. Anyway, so we have a sense of what a slashable event is or what causes a slashable event. The other thing probably helpful to mention about slashable offenses, and you may have kind of already got a sense of this, the specs and the implementation of the specs can't distinguish between a malicious intent and an honest mistake. And I would argue that I think it's very likely that every slashable offense we've seen to date is a mistake. It's not malicious. People aren't attacking Ethereum. And the numbers, generally speaking, in terms of the number of validators that commit a slashable offense in the same time window is quite low. And so to me, all of this, like, to me, it's clear that these are just mistakes. But it's important to keep that in mind. And I would say that the recipe for a slashable event is basically running your validator keys in two or more locations at the same time. Or running, let's say, locations is probably not a great term to use, instances, running multiple instances of your validator keys. That's a recipe for disaster, a recipe for a slashable event to occur. So what you sometimes can see is if you have a primary server where you're running your validator keys and you also have a failover, a backup that turns on automatically, your primary goes down, your backup comes is activated automatically, and then unbeknownst to you, your primary comes back online. And now you've got two instances of the same keys being run at the same time. And you know, you can see there are these reports you can see online from various slashable incidents that have occurred where folks have decided to publish what's happened to them. That there's a flavor of that often going on. But the key concept is two or more instances of validator keys running at the same time. And that's really where you get these incidents. So we have a decent sense of what a slashable event on Ethereum looks like. We see how that can happen, and we have some more details about the kinds of data that goes into an attestation, the kind of checks that are done for a slashable event. But what actually happens to a validator when it is slashed, when it's caught committing a slashable offense? Well, there are four things. First, the exit process for that validator is begun, and an initial slashing penalty is levied on that validator. In other words, they have some of their ETH taken away. There are two other things that happen. After that initial slash, that initial penalty is taken, the validator enters what I call limbo state for 36 days. I believe it's 8,192 epochs, but 36 days where the validator accrues penalties. What it looks like is, from the network's perspective and from the validator's perspective in terms of the penalties that are levied, it looks as if the validator just shut off their machine. They shut off their client and they're not doing anything. those penalties accrue regardless of what the validator does. Okay, so even if attestations are made in a timely and correct manner, that penalty is still going to accrue. It's a result of being slashed. So 36 days of that penalty. Over that entire period, if your validator has 32 ETH on it, that penalty is going to, the amount of that penalty is going to be about 0.05 to 0.07 ETH. That number depends on other things like the amount of stake on Ethereum, and you can do a calculation for that. We'll see that as we run through the specs, and I'll highlight those things for you. But generally speaking, the total penalty over that 36-day period is going to be about, again, 0.05 to 0.07 ETH. The other thing, the fourth thing that happens 18 days after your slashable offense. In other words, halfway in to that 36-day window, there's something called the proportional slashing multiplier. The idea of the proportional slashing multiplier is to prevent attacks on Ethereum. And so the greater the proportion of validators committing a slashable offense, the higher the penalty. So, and I'll show you where this is in the specs where you can see these parameters, but basically as of today, and it's been this way for quite a while, if let's say 5% by stake on Ethereum have committed a slashable offense in your window, and I'll explain that in a second, in your window, then the penalty for you is 3 times 5%. In other words, 15% of your stake is taken from you. And remember, that happens 18 days into your 36-day limbo period. So what Ethereum is doing is basically saying, we're going to take a 36-day window centered on when you committed your slashable offense. In other words, you go 18 days before, 18 days after, and looks at all of the stake that's committed a slashable offense. And it calculates the proportion of all stake that's committed a slashable offense. So 18 days before, 18 days after, and then it levies your penalty on you 18 days into your 36-day period. So there are kind of two 36-day windows. One is centered on when you committed your slashable offense. The other one, which is your limbo period, begins when you've committed your slashable offense and goes 36 days out. So again, halfway through that period, your proportional slashing multiplier is levied. So those are the four things: exited, initial slashing penalty, 18 days of limbo period where you incur downtime penalties amounting to about 0.05 to 0.07 ETH for a 32 ETH validator, and then finally the proportional slashing multiplier, which actually is incurred halfway into your 36-day limbo period. So those are the broad things that happen. And as I mentioned, the overall penalty post-Pectra is lower than what it was pre-Pectra. There are two things that are happening. First, the initial slashing penalty has gone down considerably post-Pectra, but the proportional slashing multiplier has gone up in some cases. Those two effects taken together means the overall penalty has gone down in most cases. It's going to be the same or lower than it would have been pre-Pectra. There are no cases where it will be higher. So again, I'm going to create a worksheet where you can see for various amounts staked, pre and post Pectra, and proportion of network that's committing a slashable offense. I'm going to link a spreadsheet where you can actually see the difference between the two. So let's get into it. The specs that are going to be of most interest to us will be phase 0, Bellatrix, and Electra. So what I'm going to do is I'm going to go through each part. I'm going to focus mainly on the initial slashing penalty and the proportional slashing multiplier. I will show you briefly the where you can see the limbo period where you're incurring that penalty, but that has not changed. So I'm not going to spend a ton of time there. I'm just going to spend most of my time on the things that have changed the most. So first, let's look at Bellatrix. And you can see the initial slash. So slash validator is a function for the initial slash. Okay, so let's go through step by step each thing that happens, beginning with slash validator. The slash validator function takes care of the first two pieces. The exit process has begun and the initial slashing penalty is levied. And if you want to see where this function is called, you can actually just search in the specs. Either probably phase 0, not Bellatrix, but phase 0. You could also search in Bellatrix just to see if there have been any modifications. If you didn't watch my last video, a reminder about the specs. Phase 0 is the only complete set of specs. All of the other forks that you would have seen, so Altair, Bellatrix, Deneb, etc., the specs that are listed are only for the parts that have changed. So it's not a full set of specs. So just bear that in mind when you're looking for different functions and things like that. Anyway, slash validator does the first two things. Initiates the exit and levies the initial penalty. And you can see the exit here. Initiate validator exit. And here's the decrease balance where the penalty is levied. One other thing to highlight before we get into the slashing penalty is the withdrawable epoch. And that's also set in this function. So when I talk about that 36-day limbo period, this is what we're talking about here. Or I should say it's related to this. And bear in mind, there are two different time frames you need to think about when a validator is being exited and withdrawn. First is the time to exit. So there can be an exit queue. Ethereum only allows so much ETH to be exited from the validator set at a time. And so what can happen is you'll see a queue, both on the activation side and on the exit side. And so you have to wait if there's a queue to be exited from the active validator set. And while you're waiting in that exit queue, you still have to perform your duties as usual. After you exit, there's a withdrawability delay. So there's a baked in delay. And then there's also, it takes time for your ETH to be swept to your EOA. What this is doing is it's basically setting a withdrawability delay, and it's incorporating this epochs per slashing vector, which is going to be that 36 days. In fact, we can see that. Let's go specs. Should be set as a parameter. It's either 8,192 epochs or 8,196. I always mess those up. Here it is. Oh, no, wait. That's slots, not epochs. Here it is. Epochs per slashing vector, 8,192, or 36 days. So that is, remember, epochs per slashings vector. Let's just go back to where we were. Back again, back again. Here we go. And so you can see the validator may exit the active set long before that, and likely will. I don't think we've ever seen an exit queue that's 36 days. But actually, maybe that's possible. Anyway, they won't be withdrawable until that 36 days has elapsed. And by the way, while they're waiting to be withdrawable, they're also accruing those penalties that we talked about. So anyway, that's just an aside thing. You can look more into this, but that's not really the purpose of this section of the video. Anyway, the exit process has begun for the slash validator, and here is the slashing penalty. Slashing penalty, validator effective balance, and remember that this dot effective balance will return the balance, the effective balance of the validator in GUI. So if you have a validator with 32 ETH, this will return 32 billion GUI, which is 32 ETH. Floor division, min slashing penalty quotient Bellatrix. Okay, so let's take a look real quick at that. 32. So this penalty, 32 billion, oops, 32 billion divided by 32 gives you a billion. A billion GUI is 1 ETH. So if a validator has an effective balance of 32 ETH, it will have 1 ETH taken from it. As a reminder, what we're looking at right now are Bellatrix. That is pre-Pectra specs. Okay, so let's take a look and compare the pre-Pectra specs, Bellatrix specs, to post-Pectra and see the change. And as a reminder, this amount right here has increased, which means the total penalty, because the denominator is increased, this whole penalty has gone down. But let's actually look at that. So if we go Ethereum specs, and remember that min slashing penalty quotient Bellatrix or whatever it's called was 32. And you'll see that it's gone up to 4,096. Here it is. Min slashing penalty quotient Electra is 4,096. So if we look at that, we'll see the same function. And you can see everything else is the same. There's still initiate validator exit, still setting the withdrawable epoch. And then here's that same penalty. Same thing. Validator.effective balance, floor division, min slashing penalty quotient Electra. Now instead of 32, the quotient is 4,096. So when you think about that as a fraction, 1 over 4,096 is 128 times less than 1 over 32. Practically speaking, the penalty, if you have a validator with an effective balance of 32 ETH, the penalty is going to be about 0.008 ETH versus 1 ETH. So you can get a sense of how much less that initial slashing penalty is. In fact, one of the options available to validators with Pectra is to carry a much higher balance. You can increase your max effective balance from 32 to 2,048 ETH. If you were to carry a validator with an effective balance of 2,048, the penalty would be half an ETH. So even if you increased your balance on your validator such that you have an effective balance of 2,048, the penalty is still going to be less. The initial slashing penalty is going to be less than what it would have been pre-Pectra with a validator of 32. So again, pre-Pectra, as we just saw, the penalty was 1 ETH. Post-Pectra, with 32 ETH, the penalty is now just 0.008 ETH, or your validator's effective balance, let's say you have 32 ETH, divided by 4,096. But even if you had the highest, even if you had a validator with a max effective balance of 2,048, the penalty, the initial slashing penalty, would only be half an ETH. One thing to note is that although the initial slashing penalty is decreased post-Pectra, you still incur a higher penalty if you have a higher effective balance. That doesn't change. So you can see, and I mentioned this a few times already, but if you have a validator with 32 ETH and it's slashed, the penalty is around 0.008 ETH. If you have a validator with an effective balance of 2,048 ETH, your penalty is half an ETH, which is much higher. So even though comparing pre and post Pectra, the penalty has gone down substantially, the logic is still such that the higher your effective balance, the greater the initial slashing penalty is going to be, even though it's much, much less than it used to be with pre-Pectra or Bellatrix specs. So to summarize, for the first two pieces, the exit has begun. That doesn't change. The initial slashing penalty is much less. It's 1/128th of what it was pre-Pectra. And obviously, the higher your effective balance, the higher that penalty is. But it's much less than it would have been previously. So that's the first thing. I'm going to show you the so-called limbo period, which is here. So I'm not because this part does not change. And by the way, you'll notice at the top there, Altair. Try and highlight that. No, you can see it anyway. Altair. This hasn't changed. Okay, so the limbo period that I talked about, the 36 days where you're incurring downtime, in quotes, downtime penalties, that hasn't changed. So I'm not going to spend a lot of time here, but if you're interested and you want to dig a little bit deeper, this function get flag index deltas is where you want to begin your review or analysis. And it comes down to these nested functions here. So you can see you start with a for loop. So you're basically cycling through all the validators. So what I draw your attention to is this block right here. You have an if and an else if statement. You also have a nested if, but you can ignore that. The first part of this if statement, basically what Ethereum, what the code is doing, what the specs are doing here, is cycling through all the validators that were unslashed. So the vast majority of validators, and then it's processing rewards. This second statement, though, so the first part of the if captures the unslashed validators. This block captures the slashed validators. So you can see else if flag index does not equal timely head flag. Reminder that validators have 3 attestation duties: timely source, timely target, timely head. Timely head is the only duty of those 3 that doesn't carry a penalty for failing to perform. The other 2 do. And so that's why you have this not equal to timely head, because it doesn't carry a penalty. So this condition pertains to slashed validators, and it's ignoring the timely head flag. For everything else, the penalties for this particular validator, which is identified with index, you're adding a penalty. So this is the calculation that gives you your quote unquote downtime penalty. This is where it begins. There's more, you have to do a little bit more work here to fully see this. You have to see the function that's calling get flag index deltas, and then look at a few other things here. But this is basically where you'd want to start and review this part of the specs. Again, this doesn't change pre and post Pectra. The penalties are roughly the same. But I just wanted you to see that because it is one of the things that happens with a slashable offense. So given that that's covered, let's move on to the last thing, which is proportional slashing multiplier. And that happens in process slashings. So again, just like I did when I covered the initial slashing penalty, I started pre-Pectra, that is Bellatrix specs. I'm going to do the same thing here. I'm going to start with the Bellatrix specs, and which is pre-Pectra, and then I'm going to cover post-Pectra, what it looks like today. So let's dig into this function. One thing to note, a lot of these functions will return amounts in GUI. Okay, so you have to bear that in mind as you're following along. This part here, you can look this up. This is in phase 0. You can look up the function get total active balance, but basically this function will return you an amount in GUI of all the active validators. So basically it's looking at the active stake but in GUI by effective balance. That's what this is returning you. So all the validators that are staked and active. This is the next calculation, adjusted total slashing balance. You can see it's taking the minimum. Basically, you can ignore the minimum piece. All that's doing is saying if the calculation inside, if this part right here, sum state.slashings times proportional slashing multiplier Bellatrix is greater than the total balance, that is all the ETH that's staked, take all the ETH that's staked. The way to think about that is you can't slash more than all of the ETH that's staked. It's not possible. So don't try. Just take the total balance. Okay. State.slashings, you can think about that as a vector or a list of the amounts of all of the slashings. So the balance of all of the validators that have been slashed in that 8,192 epoch or 36-day window. That's what state.slashings is. It's their effective balance. So take a sum of all of the validators committed a slashable offense by their effective balance, so basically how much they have staked, and multiply it by the proportional slashing multiplier Bellatrix. And if you'll remember, that's 3. Might as well just take a quick look. So Here you can see 3. UN64 is the type, but 3 is the actual number there. So you can see it's the sum of validators by effective balance multiplied by 3. That's what this will return. And again, the minimum is just to avoid taking more ETH than is there. The next part is where the penalties are calculated per validator and where they're also levied. You can see the initial check here. 2 things happen. First is the validator slashed. And is the current epoch plus epochs per slashing vector floor division 2 equal to the validator's withdrawable epoch. So if you remember, when I pointed out the slash validator function, where those first 2 things happen, where the validator is exited and the initial slashing penalty is levied, I also mentioned that this value is set for the validator that's slashed. When is it withdrawable? And I mentioned the epochs per slashing vector, so that 8,192 epochs. So what's happening here, this is a check to see if the validator that's been slashed is halfway through that 36-day window. It can be a little hard to see, but this is something you can, if it interests you, you can take this away and look at it. But you can see basically this is giving you that half. So is the current epoch plus 18 days equal to the validator's withdrawable epoch? And you can see if that's what that means. Another way to think about that is the validator halfway through its 36-day limbo period? If it is, see, this is the if statement, and here's the result. Okay, here's what happens. This block is calculated. And ultimately, you can see that the balance is decreased by penalty. And then you can see penalty is here, and it's defined by these things as well. So let's start from the top. Increment is 1 billion. And this, I believe the reason for using increment is to avoid, oh yeah, here we go. It actually says it right here. Factored out from penalty numerator to avoid uint overflow. So that's why you're going to see these increment being divided and then multiplied. But basically just remember this is 1 billion, okay? And you can check that, you know, and I'll just do it now. Sorry. Ethereum specs. It'd be in phase 0. Beacon chain. Let's go. Effective balancing. There it is. You can see it's 1 billion. And that's what this is. It's 1 billion. So this is relatively straightforward, but you have penalty numerator. So it's validator.effective balance, floor division, increment. So again, remember this returns GUE. So it's if you have an effective balance of 32 ETH, this will return 32 billion because it's in GUE. Floor divide, increment. So what happens is here, you're basically calculating your effective balance in ETH rounded down to the nearest whole ETH. So if this, for instance, returns, let's say, 31,500 million. In other words, 31.5 ETH worth of GUE. So 31,500 million. And you divide through by 1 billion, what you're going to get, regular division, you'd get 31.5. But because it's floor division, it rounds down to the nearest whole ETH. So instead of 31.5, you get 31. The point is, this calculation is giving you the balance, the effective balance in ETH rounded down to the nearest integer or whole ETH. So in other words, again, floor division is just divide 2 numbers, drop the decimal. Give me the round down to the nearest integer. So drop the decimals. Then you multiply that by adjusted total slashing balance, which is the number up here. And remember, that's all of the validators that have been slashed, their effective balances multiplied by 3, proportional slashing multiplier Bellatrix. And remember, at the outset, I said basically the idea of the proportional slashing multiplier is to take the proportion or percentage of stake that's committed a slashable offense in your window, multiply it by 3, and take that from you. So if 5% of validators committed a slashable offense in your window, 5% times 3 is 15%. 15% of your balance will be taken. And we're getting to that with this calculation here. Because here you can see this is your balance in ETH, rounded down to the nearest whole ETH, multiplied by this amount here, which takes into account all of the validators committed a slashable offense by their effective balance, and you're multiplying that by 3. Now, it's not yet a proportion. Okay, so at this point, penalty numerator, it's just taking your balance in ETH, in whole ETH, and multiplying it by this adjusted total slashing balance, which is basically 3 times the effective balance of other validators that commit a slashable offense. But it's not that 5%. It represents 3 times those slashed validators' balances. It's the next calculation, the next line that expresses that as a percentage, which is here. So here, the penalty is penalty numerator, which is calculated here, floor division total balance multiplied by increment. It's here where you take that penalty numerator and divide through by total balance that you get the proportion. You get that 5%. When you want to translate the balance of the validators committing a slashable offense to a percentage, that's basically what's happening in this line here. Now, multiplying by increment, multiplying back by a billion, recognize that this piece in this calculation is giving you an amount in ETH. In other words, your balance in ETH rounded down to the nearest whole amount of ETH multiplied by adjusted total slashing balance. This part, though, is not in ETH, it's in GUI. And so this penalty numerator is this weird number where you're mixing ETH and GUI, but you're getting back to a GUI penalty when you multiply through by increment. That's what's happening here. Now, this might have been confusing running you through this. What I would suggest, if you're having a hard time wrapping your mind around everything that's going on, start with this term here. Forget about the floor division. Just take a piece of paper, write this out, write it out as normal division, substitute in penalty numerator, this part right here. What you can do with some very basic elementary kind of algebra, just moving things around, what you will do is you will be able to see, and also substitute in adjusted total slashing balance. And when you move things around, you'll be able to see that basically what's happening is your balance as a validator is having a proportional slashing multiplier removed from it. And the proportional slashing multiplier is just 3 times the percent of stake that's committed a slashable offense. I know it sounds really convoluted and this kind of looks a little messy, but I promise you, or I don't promise you, but it'd likely be helpful if you start substituting things in. So start with penalty, substitute in penalty numerator. In penalty numerator, substitute in adjusted total slashing balance. And when you put all those things together, you can start moving them around and you'll be able to see things more clearly potentially. The last thing to happen is the validator has its balance decreased by penalty, which is an amount in GUI, and it's going to be equal to roughly 3 times the proportion or the percentage of validators committing a slashable offense in your 36-day window. And remember that 36-day window is centered on when you committed a slashable offense. One interesting thing to note, though, and this is going to be important when we go to post-Pectra, is that there's a conditional aspect to this calculation. So the thing to recognize, you see floor division all over the place. What happens is that if you have a validator with 32 ETH effective balance and around 1.1% of stake commits a slashable offense, that is a threshold value. Below 1.1% of stake committing a slashable offense in your 36-day window means that no penalty will apply. Above 1.1%, and you will have the proportional slashing multiplier applied. That's the conditional aspect of the proportional slashing multiplier. Again, I would emphasize we're talking about pre-Pectra. The conditional aspect goes away post-Pectra. So to see that, you just have to look here. It can be a little challenging to see because of, I mentioned all the substitution you have to do. But if you sub in certain numbers here, this will round down to 0. Because again, it's floor division. Remember, so just this part, you can substitute a number in here for penalty numerator and substitute a number in here. And you can find cases where this will round down to 0. Because again, floor division is just divide two numbers and round down to the nearest integer or whole number. In other words, divide two numbers and drop the decimal. And it turns out that if you have a validator with an effective balance of about 32 ETH and around, let's say, less than 1.1% of validators commit a slashable offense, this will round down to 0. What you can do to see that is for some state.slashings, calculate the proportion of the network that's, let's say, take 0.5%. To make it easier, just take 0.5% of the network of staked ETH. So today, I think staked ETH is around, well, let's actually look at it. Beacon chain. 35.6 million ETH staked. Okay. So for this, what you can say is 0.5% has committed a slashable offense. So for 35 million ETH, that's 175,000 ETH have committed a slashable offense. Because 350,000 is 1% of 35 million. Half of that is 175,000. So what you can do is you can substitute in here 175 million. And then multiply that by 3. Oh, sorry. And it's not 175 million. It's 175 million times a billion. Because remember, state.slashings is not in ETH, it's in GUI. So 175,000, that's 0.5% of stake, but that's in ETH. So 175,000 times 1 billion, multiply that number by 3, and then go and substitute that in. Here you can keep effective balance at 32 billion. Dividing through by increment gives you 32. Then 32 times this number we just calculated. Substitute that in for penalty numerator, and then take total balance. Remember, total balance is 35, what did we say, 35.5, 35.6. I'm going to go back now. 35.6. That's 35.6 million. So to get total balance, remember, total balance is going to be in GUI. So take your 35.6 million, multiply by 1 billion. And then if you do this division, this floor division, you'll see this rounds down to 0. And so the penalty is 0. So you can substitute in various numbers here. And in fact, if you're really ambitious, what you could do is substitute in all these values. So start with penalty, substitute in penalty numerator, and then into that, substitute in adjusted total slashing balance. And what you can do is you can isolate the percentage of the network. And then you can see, if you isolate, you can see what are the conditions where this floor division will be greater than 0. That's a different exercise. Not going to do that now. It's already going to be a long enough video. But if you're interested and you're a nerd like me and this kind of thing, I don't know, kind of interests you or whatever, you can go ahead and do that. Although I don't expect anyone would do that, but you could do that. And just to prove it to yourself, you could isolate that term and see and calculate the actual threshold value for the proportional slashing multiplier. Again, this is pre-Pectra, Bellatrix specs. The conditional aspect of the proportional slashing multiplier goes away post-Pectra. What that means is there's no longer a condition. The proportional slashing multiplier will always apply post-Pectra. So let's take a look at that. So if we go Ethereum specs, and let's go to Electra chain and process slashings. Here we go. Process, sorry, I should type out the whole thing. There we go. Process slashings. Here we go. Now, you can see the calculation, and you can see this function process slash is modified to use a new algorithm to compute correlation penalty. Now you can see the start looks the same. Total balance, get total active balance, adjusted total slashing balance, same thing as before. You're taking the minimum total balance. Increment, for whatever reason, is pushed up here. If you remember in the prior set of specs, Bellatrix, that is pre-Pectra, I think it was actually in the for loop, potentially. So but after that, this is where the calculation starts to change. The first thing to notice is this penalty per effective balance increment. You have adjusted total slashing balance, floor divide, total balance, floor divide increment. And you can see this calculation is in parenthesis. Total balance divided by increment. So the name is actually super helpful to tell you what's going on here. Penalty per effective balance increment. We're going to see this in a second, but basically what this is saying is for every amount of ETH you have, the penalty is this calculation here. So if you have 32 ETH, you would multiply this calculation by 32, and that would give you your proportional slashing multiplier. But let's actually look at the formula itself, and we can see more about what's going on. So first, total balance, floor divide increment. Remember, increment is a billion. Okay, so basically what's happening is total balance is a number that gives you total staking balance in GUE. So if you factor out a billion from that, you're going to get total balance in ETH. Again, floor division just means dropping the decimals. But again, when we look at Beacon Chain, it's not going to make a huge difference, right? So here, this would effectively be that number, 35,664,851 ETH. Now, this number would look a little different if you reported it in GUE. But basically, where is it? Here, you're effectively ignoring anything less than an ETH, which is what this floor division is doing. But basically, it's going to be that 35.6 million ETH number. That's what this is going to give you. Adjusted total slashing balance. Now, what this does, this number, remember, this is in ETH. This is in GUE. And it's just like before. Again, some state.slashings. State.slashings is a vector or list that gives you the amount, the effective balance in GUE of all the validators that have committed a slashable offense. And it sums that number up. So it gives you one number and it multiplies by 3. It's the same thing that we talked about before. This is a number in GUE, and then you divide through by the total balance in ETH. Now, I know it's a little confusing. Just looking at that in isolation, you're mixing units here. This is in GUE, and this is basically ETH. But you should recognize that you're taking the total balance of validators that have been slashed, and you're dividing through by total balance. Now, again, ignore the units for a sec because it creates a weird mismatch. That's going to come out in the wash later in the block below. But you should at least recognize that it gives you the proportion, even though the units are off, it gives you a proportion of validators committing a slashable offense. So again, I use the example of 5%. This will get you a number that is a multiple of 5%. That's the important thing to take away. And you're going to see that the units get corrected at the end, kind of like in the prior calculation. The big takeaway, though, is what I said at the outset. This gives you a multiplier. This multiplier will be applied to the validator's balance. So in other words, if you have 32 ETH, you multiply this penalty per increment by 32, and it gives you the penalty to levy on a validator. In other words, again, it's exactly what it says here, penalty per effective balance increment. So for every balance increment you have, that is the equivalent of 1 ETH, you pay this penalty. That's the way to think about it. It's a multiplier. Here's where the penalties are calculated per validator and where they're levied. So this if condition is the same as last time. So if the validator is slashed and the current epoch is halfway through that validator's limbo period, that 36-day withdrawability delay, levy the penalty. That's what this is saying. Just like last time, just like pre-Pectra. Effective balance increments is validator effective balance. Remember, this returns in GUI. Floor divide by increment. Remember, increment is a billion. This calculation, what it does, it takes a validator's balance in GUI and returns the validator's balance in ETH divided down to the nearest whole amount of ETH. So again, if you have a validator with 31.75 ETH, the effective balance increments will be 31. Because 31,750,000,000 divided by floor divided by a billion gives you 31, not 31.75. Drop the decimals. Here's the calculation of the penalty. Penalty per effective balance increment, which was calculated up here, multiplied by effective balance increments, which we just calculated here. So again, remember when I was talking about this, and it's very well named. I think it's almost intuitive when you read the name what it's doing. It's a multiplier. So you multiply for every whole ETH you have, you pay this penalty. And that's what this is calculating right here. Penalty per effective balance increment, the multiplier, and then how much ETH do you have? How much whole ETH do you have? Effective balance increments. And then decrease balance by penalty. And remember, this returns in GUI. I think that should be in, yeah, oh no, nothing is returned. Okay. But this gives you a penalty in GUI. And it'll be taken off your balance, which is also in GUI. Now, the thing to note, though, is that you don't have the same conditional aspect here. You do have floor division. Okay, so whenever you see floor division, there's a chance that there's a conditional element to something that could round down to 0. But if you look through for any realistic numbers, it's not going to happen. Here, it's not going to happen. Total balance divided by increment. This gives you total balance in ETH. And then again here, adjusted total slashing balance, floor divide by this number. This is because this is in GUI and this is in ETH. The difference here is in billions. So this also will not round down. I'm just trying to think. This will also not round down. It's a little bit challenging to see, but adjusted total slashing balance is in GUI. This calculation is in ETH, and the difference is a billion. So even if all of the ETH were staked, so even if this denominator was 120 million, if you can commit a slashable offense and you have 32 ETH, this is going to be 32 billion. So even if you're the only validator that's committed a slashable offense, so this calculation will give you, actually, I say 32 32 billion, but it's actually 32 billion times 3. It'll give you 96 billion. 96 billion floor divide by 120 million, it's still going to be a positive number. So there's no conditional aspect here. And there also isn't here. Because again, validator effective balance is returning in GUI, so it's a number in billions divided by a billion. And a reminder, the ejection balance on Ethereum is 16.75 ETH, or an effective balance of 16 ETH. I'm going to do a separate video on hysteresis. I'll explain why there's a difference. The ejection balance is 16.75, and the effective balance for an ejection is 16. It has to do with hysteresis. A balance of 16.75 will give you an effective balance of 16, but that's a separate, I'll do a separate quick video on that one. But you can see when you look at these parts, you're never going to get anything to round down, even in the case where you're the only validator committing a slashable offense with 32 ETH. There's just no place in here for this to round down and be conditional. So when I talk about, or when I said that the proportional slashing multiplier goes up, that has mainly to do with the conditional aspect of it. So those cases, as I showed you for pre-Pectra, where the penalty would have rounded down, now it's still there. Though that's the majority of cases where you see a higher proportional slashing multiplier. Again, I think what will be helpful with this is actually creating a sheet where I model this out and you can see the differences and you can see just how much of a difference there is pre and post Pectra. Because it's not, there's not one uniform calculation you can do. A lot depends on your balance. And pre-Pectra, would you have rounded down to a penalty of nothing? Or so the point is the order in which these calculations are performed matters, and that drives the penalty that you face. And so because those things have changed, there's not some simple relation that you can outline that gives you a clear, oh, okay, it's always going to be this much of a difference in penalty. So anyway, I will come up with a sheet for that, and I'll add it to the to this video so you can see. The last thing I wanted to cover is why this change in the proportional slashing multiplier. The initial slashing penalty, I think I mentioned this previously, but the idea is not to inhibit validators from running higher balances, from increasing their max effective balance from 32 to 2048 ETH, and to also not block anyone from consolidating validators. I think in my mind, that's very likely one of the key drivers of the initial slashing penalty change. But the proportional slashing multiplier change is maybe not as obvious. And I think there are actually two reasons for that. I'll share with you what the reason that core devs made this change. So this is a post. I'll link to this in the video, but here it is basically. Oops, right here. If validator effective balance equals 2048 ETH and greater than 30.024 million ETH is slashed, the overflow can occur in the first line of the following code. So this relates to how the penalty was calculated pre-Pectra. And the reason for the change is because of this overflow potential. Now this greater than 30.024 million ETH is slashed. I pointed out that today we've got 35.6 million ETH staked. So if that were to happen, an overflow, well, I imagine an overflow is a serious error, but you're basically talking about slashing all of the validators on Ethereum. So, you know, it's kind of like, yeah, it's good to be accurate and whatever, but if everyone's slashed, you have potentially bigger problems that you need to address. The other interesting thing here, in addition to this overflow problem, is that pre-Pectra, one of the drivers of the conditional aspect of the penalty is the validator's balance. So when I covered that, I didn't look at that aspect. I talked about the proportion of other validators committing a slashable offense. And I mentioned that threshold of 1.1%, below which typically for a validator with 32 ETH, the penalty does not apply, and above which a validator with 32 ETH, the penalty does apply. So I was using the proportion of other validators committing a slashable offense as the variable of interest. What you can also do is go back and do the same analysis, but hold fixed at around 1.1% of validators committing a slashable offense, and then change the validator's effective balance up and down. And you can see that variable as well will dictate whether there's a proportional slashing multiplier or not. So if you hold fixed at 1.1%, for instance, of validators committing a slashable offense, but then you assume instead of 32 ETH, the validator has 16 ETH effective balance, ignoring the ejection for a second. At that level, effective balance of 16, the proportional slashing multiplier does also not apply. However, if you had a balance of 2,048 ETH, it would apply. So the point is, had things not been changed, in addition to having this overflow issue, you also have this issue that validators would rationally look and say, well, if I carry one balance, the proportional slashing multiplier won't apply, but if I carry another balance, it will apply. So that could affect validators' decision to either consolidate validators or carry a higher balance. So by removing that from the thought process, you remove a potential blocker for validators to consolidate or carry higher balances. So that's another good reason for this change in the specs. So anyway, hopefully that's been helpful. I know it's a lot of information, but I do think it's important for folks to understand the changes between pre-Pectra and post-Pectra, and understand how the amount slashed has changed. Also, this post I will link, and it's also very helpful. It gives a good analysis of the change in calculation and how the penalty changes. So that's also very useful. But again, as I kind of outlined in my thread talking about these videos, please do reach out if you have any questions, if there's anything you want me to cover, or if there's something I got wrong. Again, I do make mistakes, and so I have to go back and change things from time to time. So please do reach out. And yeah, I'll keep releasing these videos. Hopefully they're helpful to folks. Cheers.